Okay, in the last lecture, we saw how to visualize matrix data. And there we saw how to visualize matrix data using heat maps or using clustering methods like H-cluster, this hierarchical clustering. So the heat maps were showing all the data of a matrix, and optionally they perform also hierarchical clustering. Clustering does not show them the values of the data, but reveals some relationships that the samples may have. So let's say that also this is the class BIOL476. It's genetic analysis, analysis of genetic data, and it's the material for the lecture 4 and 5. In this video, we will see how to visualize data that are related to vectors. And usual plots are the density plots, the histogram, and the box plots. We will also see the violin plots using some special R libraries. Okay, let's start. The histogram is the simplest of all these plots, so let's start with the histogram. And let's go back to R Studio. Okay, I clean this data here, I clean the environment, and let's say that we have a vector A with values from a uniform or from a normal distribution, let's say a normal one. 1000 values, they come from a normal distribution with mean 100 and standard deviation 10. Okay, this is a typo, R norm. Okay, the values are shown here, 1000 values, and you see that all of them are around 100 actually. Random values that follow a normal distribution with mean 100 and standard deviation 10. In other words, these are values that are coming from such a distribution, 100, which means that if we pick a value from this distribution, it's more possible to be around 100 and less possible to be far away from 100. Okay, now let's make a histogram of this data. It's very simple. We may call the function hist with argument A, and if we press Ctrl Enter, this will be shown here. So how this histogram works? What R is doing is that it finds the minimum value and the maximum value of these values here. So the minimum of A is, let's say, 67, and the max of A is 133. Okay, so what it does is that it takes the x-axis as x-axis the area between the minimum let's say something like 65, and the maximum, let's say 135, and splits it in a certain number of bins. By default, R is using something like 15 bins, but we can count them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 bins here. It uses a number of bins. Doesn't matter how many they are. I say it doesn't matter how they are because R actually has an algorithm to decide how many bins it wants to use based on how many values exist. Okay. So what it does then, it splits this area here into 15 bins that all of them have the same size. Like that. And so on. The size of each bin is exactly the same with any other bin. And then it counts from these A values how many values fall inside each bin. So let's say if this is 68 here, it finds how many values from these values are between 65 and 68. And let's say that there are 3 values here. Then it does the same for the other bin, for the next bin, 68, and this maybe will be 71, and finds, let's put these values here, 68, 71, and finds 5 values. Then finds here 9 values, and then here 8 values, and here 12 values, and so on. And what it does here, it puts a y-axis, and here it's 3. We'll make a plot like that, a bar like that. And here is 5. So we'll make another bar that will go up to 5, and here is 9. So another bar that will go to 9. And here is 8, another bar that will go to 8, and another bar to 12, and so on and so forth. So this is the resulting histogram. And with this histogram you can immediately see how the values are distributed between their minimum and the maximum value. So some arguments that we can modify here. Let's use the help function of histogram. So we can specify the number of breaks, the number of bins actually, this is the number of bins, by setting, for example, 20. Now we will not have 14 bins, but we will have 20 bins. Curious why R didn't change that. I suspect that it actually has an automatic way to decide how many bins she wants to have. We can even read it here probably. Breaks, one of a vector giving the breakpoints between histogram cells, a function to compute the vector of breakpoints, a single number giving the number of cells for the histogram, a character string naming an algorithm to compute the number of cells. In the last 3 cases the number is a suggestion only. So suggestion, we suggest a number 20. As a breakpoint will be set to pretty values, the number is limited to this. If breaks is a function, the x vector is supplied to it as the only arguments, and so on and so forth. So I suspect here that R actually gets this number as a suggestion by us, and if it doesn't like it, then it modifies it to something else. For example, if I could put here 10, let's see what it will do. Nothing. R doesn't like to change things, maybe. 12. Yeah, it doesn't change it. That's pretty cool. It does whatever it wants. Okay, let's leave it like that. We can, however, modify other things like the color. Col equals red, then it will become red. I'm curious about the help of breaks here, if it gives any. Yeah, nothing. Okay. If we use a vector of values here, yeah, we need to span all the values, so it will be let's say sec from 60 to 150 by 10. So here what I did is that I said I want to have breakpoints at the value 60. This will be the smallest. 150 will be the largest here, and each bin will have a size 10. This function here actually creates numbers like that: 60, 70, 80, 90, 100, and these numbers here define the breakpoints. So for example, if I want smaller breakpoints, smaller bins and more bins, therefore it can be something like that, or a size of 2, something like that. You see, if you create very small bins, then you start to lose this nice bell-like shape of the normal distribution, and the reason is that we don't have enough values, we just have 1000 values, so just by chance it might happen that this one bin has more values than the next one, even though it should not happen theoretically. If I could make this number larger, however, then it starts to look very much like a normal distribution. Okay, so a histogram is like a discrete representation of the theoretical distribution in this case, or it tries to create an empirical distribution based exactly on the data that we have. Of course, it can work with any vector. So for example, if A is like that, and then I add to this A, let's say 1000 additional values that are let's say that I add 1000 the value 110, then the histogram will be a bit strange. You see here that actually I have more values in this bin. Can add even more. Oh, cool. Wait, let's make it better. So the whole distribution is like that, and now this bin at 110 has many values. So this is a histogram of the data. Okay, let's remove this. Now, close to them, so I said previously that the histogram is a discrete representation of the data. This means that another way actually to make a continuous representation of the data, so it's like I try to fit a line here and make it look more like a distribution, is to use the function density. So density of some vector, it tries to make to fit a density line on the data. It has some arguments the most important probably is this kernel argument. However, I will not go to the details. This kernel has to do with what kind of distribution we want to fit on the data. And this argument regulates how the final distribution will look like, how smooth it will be, how if it will have peaks, and so on and so forth. So usually we use this, the default I think is this Epanesnikov kernel, but pretty often we use Gaussian or rectangular or triangular kernels. So let's see, for example, density method equals, if I wrote it correctly, and then I use a plot here, plot of this thing. It will look like that, not method, sorry, kernel, I must write here. Yeah, it will look like that. So you see here again that we have a peak at around 100, and this is because our data have more values around 100. I can change this kernel here and use, for example, the triangular to look pretty similar. You see it change a little bit, but not so much. Or the rectangular kernel. Now it looks a bit more noisy here. So if we use nothing, the plot will look like that. Now another way to do this is actually to save this kernel as a separate object. Let's say D, and then just plot D here. So the D object has some arguments, some objects inside it. I can see the objects using the str, the structure function, as it's called. So it's a list actually of 8 different things. The x values are the values that the density of the plot is approximated. So it uses 58.3, 58.4, and so on and so forth. The y value here is the approximation of the density at these points, at the x points. So for example, the density of 58.3 is 1.98 multiplied by the 10 to the minus 6. Now this function here is actually like a proper distribution function, in the sense that the area under this curve is 1. That's why here the values that you see do not play any specific role. It's not the probability to see a value around 100, 0.04. It only means that actually these values are so large in order for the area under this curve to be exactly 1, like a proper distribution function. So yeah, that's the important things about the density plot. It's also summarizes the data, so if you see something like that, you know that you have more values around 100, very few values below 80, very few values above 120. Okay, another way, another useful plot is the box plot. So if I could do a box plot of A, it will look like this one. So again, we have the following attributes here. Let's get the help to explain it. Box plot. The first argument is again the vector for which we want to make the plot. data frame or list, or something that can become like a data frame or list. Sorry, this is the X. Let's say here, for specifying data from which the boxplot to be produced, either a numeric vector or a single list containing such vectors. So this is the X. So it does not show details what this what the boxplot exactly is, but I will explain it in a second. Okay, so the description of the boxplot is the following. Here we see a box, and here we see this line and this horizontal line, and here we see this line and this horizontal line. So these are called whiskers, and this, let's call it a box. This bold line here represents the median value of the data. So the median value is the following. If I have a vector, the median value is found as follows. If I sort the values, I get the middle value, which is this 3. So here the median is 3, and here the median is 3, because this is the middle value. Okay. In contrast to the mean, which is affected by extreme values like this one. Here the mean value is much larger than 3, because this is very large value. It would be exactly the same if this would be this number, the median value is again 3. So the median value is robust to outliers, and this is the median value here. It's around 100 as we expect it to be. This line here, the lower edge of this rectangular, of this box, is called the Q1 value, is the first quartile, in other words. So we have this box, we have the median, and we have these whiskers and these whiskers here. So this is the Q1, is the first quartile. First quartile means that if I have the values, so I have the A values here, I sort them. So these are sorted values from the smallest to the greatest one. These are 1000 values, and in order to find the first quartile, it's I go to the first 1/4 of the values. 1/4 of 1000 is 250, so the value 250 should be approximately the same as the first quartile value. Something like this one, 92.9. This value should be approximately around 92.9. Which means that 25% of the data are below this line. The same way, this line here corresponds to the third quartile. This means the 70% of the data are below this line here. Or in other words, 25% of the data are above this line here. Okay, so the box contains the data that are between the 25th percent and the 75th percent. This line is the median value. Okay, now this height here from 25th to the 27th, from the first to the third quartile, is called the interquartile region, IQR. This IQR is important because it defines actually the height of these whiskers. So this horizontal line lies at the following point. It is the so this is the IQR from here to here, and this height here is the Q1, which is here, minus 1.5 times the IQR. So let's say that this is about, if this is, let's say, about 40 units, and this is something like 90, then this means that here it will be the 90, this is the Q1, minus 1.5 times the 40, which is 90 minus, this is 60. So this one should be around 30. Okay, obviously this is not 40, that's why here it goes much higher. Let's say that this is from 92 to 105. From 90 to 105 it's about 15. So let's say that this is 15 here. So this will be like that. This will be 90 minus 22 something, and this will be something like 68. 68 should be around here. Okay, well, I just made the numbers, I made up the numbers by looking at this plot. It's around there. The same applies here, and this horizontal line is Q3 plus 1.5 the IQR. So this is Q3 here, and this one is Q3 plus 1.5 the IQR. So R is doing that, and actually boxplot is doing that, because then most of the data that we have are between the two whiskers. Also, 50% of the data are inside this box. Now, every other value above this line and below this line is considered by R to be an outlier, and that's why it separately shows them one by one, like this one here. Okay, this is a box plot. It's a great way actually to visualize the data. Now, if I have a data matrix like the one that I had before, let's say that I have a matrix M equals a matrix, let's say that I have 10,000 values with mean 100 and with variance with standard deviation 10, and the number of rows is 1000. So I will have 10 columns. I don't need to specify that, because since I have 10,000 values and 1000 rows, I will definitely have 10 columns. Now I can make a box plot of M, and automatically it will make a box plot of the columns, of these 10 columns that I have here. So this is the box plot of the first column, box plot of the second column, the third column, the fourth column, and so on and so forth. And of course you see that each one of the column, the median is around 100, of course, because that's how I create the data. More or less each one of them has the same variance. I can see that because the boxes here are approximately the same. Now let's say that I'm modifying it by the following. M5, for example, equals R norm, 1000 values, the same mean, but now I have a much greater variance. So you see now that the boxes of all other plots became very small, but this box plot became huge compared to the other box plots. Okay. So box plot is another way to visualize the data. Now boxplot actually hides some information. For example, here we see that 50% of the values are around here, but we cannot see if most of the points are here or here. In order to show these kinds of information, we use the so-called violin plots. Violin plot is like a box plot, but shows information about how the data are distributed. And therefore sometimes it's more informative and more desirable than simple box plots. However, violin plots do not exist in the base package of R, so we need to import a library to use them. The usual library is the ggplot library, but it needs a separate lecture for that because it has a specific logic and so on. Therefore, I will use another library called violplot. So to install the violplot, you can just type install.packages violplot. Now you have it installed, and now we can just use the following. First library violplot to load it, and then violplot and the data that we have, and it looks like that. And you see now that you see actually the distribution of the data. It's a nice Gaussian distribution around 100 and so on and so forth. I'm not sure if violplot can, yeah, it can do that. It can also work on a matrix. So this will be a violplot of each column of the matrix. Definitely, even if I haven't tried it, we can change the color. Yeah, but I don't know which way. I must read the manual for that. But anyway, a very simple way to make violplots is to use this violplot function. ggplot, another package, can make very nice violin plots, but we need actually to learn how to use ggplot in the whole and then use it. Okay, so these are some ways to visualize data in R.